Now, what we do is, in the step 3, we remove the open interval, remove the segment uj bj from the closed interval ab. It means what we are doing is that this is our interval ab, okay, and here is the point, say u1 b1 u2 u1 v1 u2 v2 and like this. Suppose these are the points, say like un, say vn. Then what we do is, we are removing this portion. This portion we are removing. So, we are getting now, after removing a into u1, a u1, this is 1, then start with b1 u2 and like this, then start with v2 and continue this way and up to here say v. So, this set k, which is in which these things are not available, these things are not available. Okay. So, this set k forms a compact set. So, once we remove the segment uj vj from it, then the remaining set k is compact, because it is a finite union of the compact closed and compact set intervals like this. So, it is a compact set, compact is compact or compact set is okay. Now, function f is given to be continuous. Since f is continuous over k, because the point of discontinuity we have already removed. So, f is continuous over k and k is compact set. So, every continuous function on a compact set is uniformly continuous. So, f will be, so f is uniformly continuous, is uniformly continuous function on k, uniform continuous function on k, clear this one. So, by definition what is a f is uniform means, so for a given f signal greater than 0. So, for given f signal greater than 0, there exists a delta which depends only on f signal, not the point, greater than 0, such that the mod of f s minus f t, this will remain less than f signal if s belongs to k, t belongs to k and mod of s minus t is less than delta, by definition of the uniform continuity. Okay. Let it be 1. Okay. Now, let us partition, partition the interval a b as follows. Suppose P is the partition, P is the, let P is the partition x 0, x 1, x 2, say x n of AB. Then B takes such partition that each u P is a partition where uj, each uj occurs in P, each bj, each vj occurs in P, means this u1, e2, un, v1, v2, vn, these are the one of the points of the partitioning point of this interval AB, and no point of any segment uj comma bj, this open segment occurs in P. This is the restriction we are putting. We are choosing the partition in such a way that the corner points of these subintervals which are covering the point of discontinuities are basically coinciding with the partitioning point, but none of the point in between in this inside this interval are the partitioning point, are the points of the partition. This is one thing. Second thing is, in case if x I minus 1 suppose is not one of the uj, because this may be possible, the number of the points are finite, maybe the number of points are not as sufficient as the partitioning point is there. So, some of the x i's will remain untouched. So, if x I is not one of the uj, then what we do is, then we put the restriction A that the x I minus 1, that is the delta x I, this should be less than delta. This is our restriction. Okay. So, once you have partitioning this point, it means okay, now we get this. So, this is our x naught, x 1, x 2, x 3, x n and so on. Say this is A, this is B. Okay. And then we are coinciding this, say suppose u naught, u 1 and so on continue. Suppose here is u j, and after this we are not getting anything, and the points in between u j are not there, one thing. So, let us see, suppose we take any interval, clearly over any subintervals m I minus small m I, this will remain less than equal to 2m. Why? Because what is our m? M is the supremum value we have chosen. This is m is the supremum value of our interval. So, if I consider the x I minus 1, clearly because over the interval over x I minus 1 to x I, the minimum value of the function is m I, supremum value is a. So, m I as well as small m I both are less than equal to m. So, m I minus m I is less than equal to 2m. This is true for each I, for every I, this is true. And further, if x I 1 is not one of the point, if x I minus 1 is not one of the point of u j, unless this is not one of the point, then the difference between m I minus small m I, this difference can be made less than equal to epsilon by, because of this part, because function is continuous as well as uniformly continuous over the k. So, if the point x I minus 1 less than delta, if this is because we have put this, if x I is not one of the point, then this difference is less than delta. So, because of the one, this difference should be less than epsilon. So, m I minus small m I will be less than epsilon. Okay. So, that for each one is will be less than equal to epsilon. Hence, if we construct the proof upper sum minus lower sum. So, upper sum of the function f with respect to alpha over the partition the p minus lower sum of the function f with respect to alpha over the partition p. This is basically what sigma I is equal to 1 to n, say m I minus small m I into delta alpha I, which can be break up as sigma over k plus sigma over a b minus k, because the dropped interval, okay, this which are dropped. So, in this case is over k, this is less than epsilon, this is less than epsilon. So, we get epsilon into sigma of this part, but sigma of this delta alpha I is 1 to n is nothing but the alpha b minus alpha a. So, this will, and this part over this already we have function is bounded. So, m I plus m I is less than equal to 2 m, and since sigma of alpha I alpha b minus this total is less than epsilon, this is because of the continuity, this sum of this corresponding is less than epsilon. So, we get from here is that this is less than epsilon, okay, and this part will be epsilon alpha b minus alpha है plus 2 m epsilon, but epsilon is arbitrary, is arbitrarily small number. So, this shows that the right hand side will go to 0 and the left hand side. So, f will be the element of f alpha. This is what proves that. Okay. So, this is what proves. Now, another results also which is interesting. The result says suppose f is in R alpha on the closed interval a b, Riemann stress integral with respect to alpha over the interval a b, and f is bounded function bounded by say m in capital M. Phi is continuous on the closed interval m and capital M. This is phi. Then and h x is phi of f x on the closed interval a b, Then this result says the h belongs to R alpha, that is Riemann stress integral on a b. So, if function f is Riemann integral function and phi is a continuous function on the that is the where the function have a range set, range of the set f is interval, then the composition of this function, continuous image of a Riemann stress integral function will be Riemann stress integral. That is what it says. Okay. So, this is just like that. Here we are taking this function, this is our interval a b, function f is given. So, here is our m and capital M, where the function f is attains the minimum and maximum value, and over which the function h is defined. Okay. So, what is a, when you combine the phi composition f x, then it will transfer directly from here to here, which is h composition h x equal to phi composition f x. And if this is in R L, this is this function phi, this is phi, sorry, this is phi, and if this phi is continuous and this is continuous, this is in R L, R alpha, then our h will be in R alpha. That is what it is. Okay. So, let us see the proof of it. Choose epsilon greater than 0. Okay. Now, given that phi, since phi is continuous on the closed interval m and capital M, so it will be uniformly continuous. Over this interval m and capital M, because every continuous function over a compact set is uniformly continuous. So, by definition epsilon we have already chosen. So, let us choose the delta. So, for this epsilon greater than 0, which is chosen earlier, there exists a delta greater than 0 such that Now, I am putting the restriction on this delta is smaller than epsilon, because this is any delta is true, then all the delta which are less, putting delta to be less than epsilon, this image will go there. Okay. So, let us take the delta to be less than epsilon, and phi of s minus phi of t is less than epsilon if mod of s minus t is less than equal to delta. What I say is, for the, because phi is uniformly continuous. So, for any epsilon greater than 0, there will exist a delta such that image of this any point in which satisfy this condition must fall within this range. Now, suppose I take delta which is greater than epsilon, then I can pick up another delta which is smaller than this, less than epsilon. So, again this image will fall here. So, nothing, we are not losing anything, but it will be advantageous while proving the whole theorem. Okay. Now, further, since f is given to be an element in R alpha, so by definition the result a necessary and sufficient condition for a function to be a Riemann stress integral, or if you in the class of this, if there exists some partition for a given epsilon, there exists some partition such that upper sum minus lower sum is less than this. So, let f belongs to this, then there is a partition, say P x naught, x 1, x 2 and x n of A B, f A B such that the upper sum of the function f with respect to alpha minus lower sum of the function f with respect to alpha over the same partition is less than, say, delta square. Clear? So, this we are getting. So, let it be equation 2. Now, over the sub intervals we have, let x I minus 1, x I plus, this is the sub interval of this partition A B, this is the partition A B, this is up. Now, here the function attains this minimum value, say m I, and the maximum value is suppose capital M I. So, let m I and capital M I is the supremum of the function f x when x lies between x I minus 1 to x I, while the m I, small m I, is the infimum value of the function f x when the x lies between x I minus 1 to x I. Clear? Let be this one. Now, function h is defined, since h is defined, because whatever the result is, that h is, yeah, f is Riemann integrable, f is this, and phi is continuous function, phi is continuous on this, and h is a function which is basically phi of h f x. So, what are the range of f, h is defined on it. So, basically the h is defined on on m and capital M. This is. So, in this case, when you partitioning this m, say m and capital M, and suppose I partition it, say m naught less than m 1 and so on, say here is m n equal to m. So, if we picked up the, say, m I minus 1 and m I. Now, in this case, when you consider the upper and lower bound for the function h, then we say, we denote this as, let us denote, let m I star is the supremum value of h t. I am using the t, where t lies between m I minus 1 to m I, and small m I star is the infimum value of h t when t lies between m I minus 1 to m I. Is it not? Just I am taking this one. Now, so this is our interval a b. Here I am taking one say sub interval xi minus 1, and here is say suppose images. So, this is our say m, and here is capital M. Say this is our. So, basically this will be the all the functions will be somewhere here, clear. In fact, this is this one like this. So, here is now we are dividing here, and then h is defined over is h is defined on this side. Okay. Now, let us choose the part. Suppose for I divide the number 1, 2, 3 n into 2 classes. First class is A, 2 classes A and B as follows. When I belongs to A, for I belongs to A, our choice of delta shows I belongs to A means that is if I belongs to A, for I belongs to A, or for I belongs to A, if or just I belongs to A if mi minus small mi is less than delta, and I belongs to B if mi minus small mi is greater than or equal to delta. So, this will be like this. Now, picked up now class 1. So, for I belongs to, so for I belongs to A, what is our choice? When I is in A, the mi minus small mi is delta. Okay. So, in this case, what is the mi star minus mi star small mi star? This will be, because phi is what? Phi is uniformly continuous. So, if I belongs to A, it means it satisfies this condition. Once it satisfies this condition, then because the h or phi is defined on what? On this interval. So, it satisfies this condition. Therefore, the difference of this mi minus small mi star must be less than epsilon. So, since our I belongs to this, so our choice of delta shows that the mi star minus small mi star is less than, and this follows from this equation, that is the relation. I will say the relation is say x star. Okay. So, it follows from the relation star. Okay. So, nothing by this. So, first thing, and if for I belongs to B, where this is greater than equal to delta, we have in this interval the mi star minus small mi star is less than equal to 2k, where k stands for the supremum value of the phi when t lies between m and capital M. So, just supremum value, and since it is greater than, so use the condition 2, where condition 2 is this condition we have taken, that is mi minus delta square. Where is that delta square condition? So, this is condition 2. This is our condition 2. This mi sigma of mi minus mi small mi delta alpha is less than delta square. So, use the condition 2. So, use 2. Then in that case, the u p f alpha minus L p f alpha. This is what? This is sigma mi minus sigma mi minus small mi delta alpha I is 1 to n. But if we take and this is given to be less than delta square, this is given to be delta given. Now, if I take the only for sigma mi minus small mi delta alpha I over the set B only, then obviously it will remain less than delta square, because this sum is smaller than this. So, it is less than delta square, but this will be greater than equal to what? Over B, this is greater than equal to delta. So, it is delta sigma I belongs to B delta alpha I. Okay. So, what does imply? That implies that sigma delta alpha I when I belongs to B is basically less than delta. Let it be 3. Okay. Now, consider the partition. Now, consider the upper sum of the function h with respect to alpha minus the lower sum of h with respect to alpha, and this we can divide in two parts when I belongs to a mi star minus small mi star delta alpha I plus when I belongs to B mi star minus small mi star delta alpha I. Okay. Now, see, this will be mi star minus a when I belongs to A. We have already justified this is less than epsilon. So, this is basically less than epsilon, and then delta alpha I will be remain less than the sigma of delta alpha I is nothing but less than alpha b minus alpha a. So, we get this part. Okay. The second portion is this entire thing is less than 2k, because this is 2k. So, it is less than 2k, and then over B the sigma is less than epsilon, sigma is less than this delta alpha I when you choose what is that? Sorry, delta, sigma is less than delta. So, it is delta. So, once it is delta, but delta is less than epsilon, this is our choice in the very beginning of this we have taken delta to be less than epsilon. So, we can choose the delta outside. So, we get the p h alpha minus L p h alpha is less than equal to epsilon outside. What you are getting is alpha b minus alpha a plus 2k. But epsilon is arbitrary. Since epsilon is arbitrary, so this shows that satisfies the necessary sufficient condition of that theorem. Therefore, h must be in RL. Some few properties of the Riemann stresses integrals. We will list the proof property, and proof 1 or 2 will be good enough. Now, if f1 is a Riemann stresses integral with respect to alpha, f2 is a Riemann stresses integral with respect to alpha on the closed interval a b, then the sum f1 plus f2 will also be a Riemann stresses integral with respect to alpha, and CF will also be a Riemann stresses integral for with respect to alpha for every constant C, and the integral a to b f1 plus f2 d alpha, the Riemann stress integral, the sum of it will be sum of the integrals f1 d alpha plus a to b f2 d alpha, and C times f d alpha is C multiplied by a b to b f d alpha. So, this is the first result. Second result says, if suppose f1 and f2 are the two Riemann stress integral, if f1 and f2 are the two functions such that f1x is less than equal to f2x on the closed interval a b, and they are also Riemann stress integral, and then integral a to b a to b f 1 d alpha is less than equal to integral a to b f 2 d alpha. Of course, where f 1 and f 2 both are in alpha, all alpha. Okay. Third is third property is if f belongs to R alpha, that is Riemann stage integral on the closed interval a b, and if a is less than c less than b, then f is Riemann stage integral on the closed interval a c as well as on c b. Means if we divide that a b into two parts a c to c b, then over each subinterval function f will remain Riemann stage integral with respect to same alpha, and the value of the integral will be the sum of these two, and integral a to b f d alpha is the same as a to c f d alpha plus c to b f d alpha. Fourth property is if f is a Riemann stage integral with respect to alpha on the closed interval a b, and if the function f x is bounded by m on the closed interval a b, then integral a to b f dx f d alpha into f d alpha modulus this is less than equal to m times alpha b minus alpha a. Okay, modulus of this d alpha. Then E property, if f is Riemann stage integral with respect to the monotonic function alpha 1, and f is a Riemann stage integral with respect to monotone function alpha, means f is Riemann stage integral with respect to the two monotonic functions alpha 1 and alpha 2 respectively are there, then f will remain Riemann stage integral with respect to the sum of these alpha 1 plus alpha 2, because if the alpha 1 and alpha 2 are monotonic increasing, the summation will also monotonic increasing. If they are monotonic decreasing, they will also be monotonic decreasing, and hence integral of f alpha 1 d alpha 1 integral f d alpha 1 plus alpha 2 over a to b is the same as a to b f d alpha 1 plus a to b f d alpha 2, and if f is Riemann stage integral with respect to alpha, and c is a positive constant, then f is Riemann stage integral with respect to c alpha, and integral of this a to b f d c alpha is c times a to b f d alpha. The proof of these results property follows by using the definition. The property is also which we just mentioned. If f is in R L and G is also in R alpha on the interval a b, then the product of this is in R alpha. Then second part is if mod f belongs to R alpha and modulus of integral a to b f d alpha is less than equal to integral a to b mod f d alpha and less than equal to. The proof is based